Hi there. Today I want to go through some basic or epidemiology hacks in R. These are really basic things, starting points, nothing getting into the more sophisticated or advanced material, just some basic stuff. And I'm going to start out today by just generating a data set. These are random data I'm generating. In the structure of these data, I'll just show you. These are case control data. This is not an uncommon, simple data structure that you might get having collected data in some sort of epidemiological study. You have cases and you have controls, and you have exposed and unexposed. So if we look at the case data, the case control data, you see a series of ones and zeros. The ones we might characterize as the cases, the people who, let's say, have a disease, and the zeros would be those who don't. And exposure works the same way, except the ones are the people who are exposed and the zeros are the people that aren't. So I've generated some data, and I've generated data in a way that exposure and status are correlated with each other somewhat. So then I take these data, these vectors here, and just assemble them into a data frame. And we can see in the data frame we've got some cases, we've got some controls. And that the cases are the ones, the controls are zero, exposed are the ones in the exposure variable, and the zeros are the not exposed. Now this is not in a tabular format. This is a natural way to collect the data and analyze it under many circumstances, but one thing you might want to do is to simplify it and turn it into a 2x2 table. So if you've taken an introductory epi course, you're probably used to the idea of a 2x2 table. And here we can just create this, take all these data and bring them together into a little table. So you see here we have 8 cases that were exposed, 35 non-cases that were not exposed, 36 cases that were not exposed, and 21 controls that were exposed. So you can, I think that's how it is. I'm not sure which is column or which is row here. It doesn't particularly matter. So once you've got data, so we've turned this data frame into a data table, a 2x2 data table, just using this little table function. Now maybe there are some formal tests that I might want to conduct when you have data in this 2x2 format, a chi-square test or this exact test if the cell numbers were too small. And you get in there, you actually get a number of things. You have this test that effectively the rows and the columns of that table are independent of one another. And you also get an odds ratio. And the odds ratio is telling us something about the relationship between exposure and status as either a case or a control. So that's what this odds ratio here is measuring. So this is basic descriptive stuff. Increasingly, people aren't as interested in that as they used to be, especially now that you have computers to do the work. And so we can also take the same information and model it. So we can estimate that association in a logistic regression model here. And we get these effects which are proportional to the odds ratio. That's not what this actually is. You have to convert it, exponentiate it to turn this into an odds ratio. But this is basically tells us about the association between exposure and case status here. And then you've got this other information that you can look at if you're interested in it. If we want, we can take a look at the coefficients specifically. So these are the coefficients from that model. There's one coefficient of particular interest, and this is the exposure variable, because this is the thing that if you're doing some basic population-based epidemiological study, you may be interested in the relationship between the exposure to some, let's say, environmental hazard or something else, and this health outcome. And this is what you might focus on. Now, if we can turn these coefficients into odds ratios, like I mentioned a second ago, just by exponentiating them. So here I'm generating the same. If you scroll up, you'll see that this is basically the same odds ratios we got out of the calculation from the 2x2 table. In this case, we're getting it out of this logistic regression model by just exponentiating that coefficient, this one here, with the following code, this little snippet of code. And we can do the same thing to the standard error here. This is just giving us exponentiating the standard error. And then we can actually calculate confidence intervals out of these data fairly easily. And this is all code that you'd probably reuse. You'd write it once and then just kind of reuse it as needed. Here I've generated the confidence intervals around these odds ratios, the lower bound and the upper bound. In the standard way, here we're looking at we're assuming some things about the distribution of the odds ratio, but we don't need to worry about that too much now. So that's some basic things, how to generate and measure of association between exposure and status as a case or control, using some fairly standard tools that you might see in epidemiology. Another thing we can do is, which I think is also useful, is to, we just sidestep this a little bit, is to play around with the concepts of attributable, absolute, and relative risk. So this is something that also in a basic kind of epidemiological application it's worth knowing about. So here I'm just going to create, I've created two rates, the absolute risk in an exposed group and an absolute risk in an unexposed group. So think about this as the risk of an event happening in two different groups of people. For example, the exposed group could be people who eat unpasteurized milk, let's say, or consume unpasteurized milk, and these are the unexposed people who do not consume unpasteurized milk. So these are the rates of some illness or adverse health condition associated with exposure. If we have population data, so this is not case control data, but if we have population data, if we have these rates, we can actually calculate relative risk. So the relative risk basically tells me how much more likely it is that this group here is going to be sick, the exposed group compared to the unexposed group. And if we just highlight this and run it, we'll see that the relative risk is 1.47. This means that the exposed group, if you're in the exposed group, you have a 47% chance increased risk of getting the disease. We can also calculate attributable risk. Attributable risk gives us a sense of how much of the risk is actually attributable to exposure. And this is often important if the condition you're looking at is very rare. Relative risk doesn't really account for how rare a condition is. It can be a little bit misleading. In this case here, we're seeing about 3.9. This is telling me there's roughly 3.91 cases due to exposure for every 10,000 people. So I look at this rate, subtract this rate, the exposed rate minus the unexposed rate, multiplied by 10,000, and the result I get is 3.91. That basically means that there are 3.91 cases for every 10,000 people as a result of exposure. That can be useful. And then the last thing I'll just talk about here is to take the same idea, but to turn it into this risk fraction. So let's say I want to talk about it as a percentage. Here, the risk fraction tells me what, in this case, proportion of the risk is due to exposure here. So I've got the absolute risk in the exposed group minus the unexposed divided by the exposed group. So what proportion, what is a fraction of illness caused by exposure? And that gives me, here I've got that number here. So this is just some basic epi stuff, nothing particularly sophisticated, and I've not gone into a lot of detailed description here, but should give you a sense of how it works if it's of interest to you. Bye.